Okie dokie, I'm going to go over some GCSE Combined Science core practicals. Now, these core practicals come up as 6-mark questions, and this is specifically for Edexcel in terms of what paper these particular core practicals are going to be on. But these core practicals will come up for any exam board, because all exam boards, they all teach the same content. Just check and see which particular paper these topics might pop up on for you. So what you might get asked about on paper 2, you'll get asked about investigating resistance, a couple of parts for that, investigating densities, investigating water, so that's specific heat capacity, and investigating springs. Investigating resistance. If you want to try this core practical before I tell you the answers, pause the video now. And here's the answers. Now, bearing in mind that investigating resistance, there's sort of 2 parts to it. So you could get asked either part 1 or part 2, or technically they could ask you both. So part 1 is about investigating resistance in a filament lamp and a resistor. Describe how to measure current and potential difference in a circuit. You may use a labeled diagram. So you'd have to add a voltmeter to measure voltage in parallel with the component. So if we quickly drew a circuit, and there's a resistor, you'd have to have your voltmeter across in parallel to the component. And you'd have to add an ammeter to measure the current in series with the component. So for example, you could pop the ammeter in there. You could pop it in anywhere you wanted along the main part of the circuit. State the equation that links current, potential difference and resistance. So that's Ohm's law, which is voltage equals current times by resistance. V equals I times by R. Sketch a diagram on how you would measure the current and potential difference in a resistor. So that's exactly the circuit I've drew up here. So a voltmeter in parallel with the component, and an ammeter to measure the current in series with the component. Results below show the potential difference and current through a resistor. Calculate the resistance of the resistor. So remember, to get the resistance, you do voltage divided by the current. So pick any values you want from the table. So for example, to get the resistance, you could take V divided by I, when V is 1, and I, the current, remember this is current I, and that's V, is 0.3. So 1 divided by 0.3 is 3.33 ohms. Or you could take any other values you wanted. So for example, we could take our V value when it was 2, in which case our I value would be 0.6. And if you do 2 divided by 0.6, you come out with the same answer. And that's because it's a resistor, or otherwise known as a fixed resistor, because the resistance is fixed. It doesn't change. Describe the relationship between potential difference and current in a fixed resistor. As you can see, as the voltage is getting bigger, the current is also getting bigger. And if V doubles, I doubles, so always look for that to see if it's directly proportional. So for example, if the voltage doubles from 1 to 2, if it's directly proportional, the current should double from whatever it is to double that. So from 0.3 to 0.6. Let's try that again. What if we doubled it from 2 volts to 4 volts. It should also double from the 0.6 volts to 1.2 volts, and it does. So that's how to tell if something's directly proportional. And here's investigating resistance, part 2. And this time it's investigating the resistance of a filament lamp in a series and parallel circuit. If you want to have a go before I show you the answers, pause the video. And here's some possible answers. Describe how current flows in a series circuit. So remember, current is a flow of electrons, and it'll go from one side of the battery to the other side. Remember, electrons are negative, so they'd come out of the negative side of the battery, which is the small side, and they will go round the circuit and go into the positive side. The current is the same size all around the circuit, and that's because there's only one path in a series circuit. Describe how current flows in a parallel circuit. So once again, current is a flow of electrons from one side of the battery to the other side. This time the current can split up when it reaches a junction in the circuit because there's more than one path. For example, down here. So as the electrons come out, they meet this junction here and they've got a choice. They either come across this top branch or they keep going down the bottom branch. So the current has split up. The potential difference across the battery was 6 volts. If the potential difference across bulb 1 was 3.5 volts, state the potential difference across bulb 2. So if we are putting 6 volts into the circuit and the voltage across bulb 1 is 3.5 volts, well, what goes in must come out. So if we take the 3.5 away from the 6, we'll discover that this is 2.5 volts. Describe what would happen to the current if another filament lamp is added to this circuit. Okie dokie. Each bulb has got resistance, so the resistance of the circuit will increase, which will cause the current to decrease. Remember, we use resistance to control the size of the current. There are more bulbs for the voltage to be shared with, so each bulb gets less voltage, so the bulbs will be less bright. So for example, if we popped another bulb in there, you might have 2 volts on there, 2 volts on there, and 2 volts on there, which equals the 6 volts. So each bulb would be dimmer because they get less voltage. The potential difference across the battery in circuit E was 9 volts. So that's this. If the potential difference across bulb 1 was 9 volts, state the potential difference across bulb 2. Well, in a parallel circuit, the voltage across each branch is the same as the voltage across the battery. So if that's a 9 volt battery, you're going to have 9 volts across this branch. Now there's only one component in the branch, so that bulb gets all of the voltage. And you'd have 9 volts across this branch, so that would also have 9 volts. So the voltage for components in parallel is the same. So bulb 2 will have 9 volts on it as well. In circuit E, the current leaving the battery is 0.82 amps. So 0.82 amps coming out of the battery and going down there. The bulbs in the circuit are identical. So that means this path here has got the same resistance as this path here. State the ammeter reading of bulb 1 and 2. Well, if both paths are exactly the same, then the current is going to split evenly. So you'll end up with half of 0.82 coming this way, which is 0.41, and you'll have half of 0.82 coming this way, which is another 0.41. So this current plus this current has to equal the original current. Explain which circuit would have the lowest resistance. So that's out of circuit E and D. The parallel circuit, because there are more paths for the current to travel down. This allows more current to flow, which reduces resistance. R, resistance, equals V over I. So if the current increases for the same value of V, the R will decrease. So we're assuming that these two bulbs here were the same as these two bulbs here. So just for example, if that was 10 ohms of resistance and this was 10 ohms of resistance, that would give a total of 20 ohms of resistance. Whereas across here, if that was 10 ohm resistor and that was 10 ohm resistor, it would actually be the equivalent of only 5 ohms, so half, because you've got the two branches. Now you no longer have to calculate the resistance in parallel at GCSE level, but just know the more branches that you get, the resistance gets smaller. Just remember that. This next core practical is called Investigating Densities. Pause the video if you want to try it before I go over the answers. And here's the answers. State the equation to calculate density. So density is mass over volume. Make sure you know the units. Mass is in kilograms, volume's in meters cubed. So density is kilograms per meter cubed. Explain in terms of particles why a solid is more dense than a liquid. The answer would be something along the lines of: the atoms in a solid are bonded together, so they are very close together. The atoms in a liquid are not bonded together as strongly, so are spaced out a little bit more. Method. Describe how to calculate the density of a cube. Now a cube is a regular shape, which makes it easier to measure. Measure the mass of the cube with scales, so mass top pan balance would be a detail. Measure the volume of the cube with a ruler, that's the detail, by measuring the length times by the height times by the depth, and multiplying them together. So the volume would be length times by depth times by height. And then use density equals mass divided by volume. So sometimes that itself can be worth 4 marks, 5 marks, something like that. Describe how to calculate the density of an object with an irregular shape. So that could be any kind of funny looking shape. Once again, measure the mass of the cube with scales. For example, a mass top pan balance, or mass. Then we need to get the volume of the cube and get that with a displacement canister. Now a displacement canister has got one of these spouts, And what you do is you fill it up with water up to the spout. And then when you plop your object in, the water rises and you'd collect the water that got displaced in the measuring cylinder. And whatever volume of water that is there, let's say it's 10 centimetres cubed, that would be the volume of your object. And then finally use density equals mass over volume, just like before. And again, that could get you 6 marks in an exam, or 4 marks. Describe how calculating the density of a liquid would differ from calculating the density of a solid. So I've just explained how to get a solid when it was a uniform or regular shape, or when it was an irregular shape. So to get the density of a liquid, we would put a measuring cylinder on a mass top pan balance and press the tare button to reset to 0. So there's your mass top pan balance. Put the measuring cylinder on there. Now, you press the tare button so that it goes back to 0 grams. Then pour the liquid into the measuring cylinder and this will tell you the mass. So if I fill this up with liquid, it might now go to, say, 10 grams. So obviously the mass of the liquid is 10 grams. Now the beauty of this is by reading the measuring cylinder, it'll also tell you the volume. So if that's said a volume of 20, well, you've got your volume, which was 20. And then just calculate your density by doing the mass, which would be like 10 grams in this case, divided by your volume, which I said was 20 centimetres cubed. And that would come out as 0.5 grams per centimetre cubed in this particular case. Okay, what about possible questions? So 0.5 kilograms of water fills a 500 centimetre cubed flask. Calculate the density in grams per centimetre cubed. So density is mass over volume. Pop your numbers in and out comes the answer. The piece of wood is 1 metre long, 20 centimetres wide and 5 centimetres thick. It has a mass of 7 kilograms. Calculate the density. So it's 20 centimetres wide, it's 5 centimetres thick, and it's 1 metre long. And that's 7 kilograms. So density is mass over volume. So your mass was 7 kilograms. Now to get the volume, we're going to need to multiply the length by the width by how thick it is. And make sure you convert. If that's in metres, then that needs to be in metres as well. And so does that, because they wanted it in metres cubed. So if you divide that by 100, that'll convert centimetres into metres, and we'll divide that by 100 as well to convert that from centimetres into metres. And your answer came out as 700 kilograms per metre cubed. So if you had a massive metre cubed block, that would be 700 kilograms, which sounds about right. Here's a core practical on investigating water, which is to do with specific heat capacity. Pause the video if you'd like to have a go before I go over the answers. And here's the answers. Define specific heat capacity. Well, it's the energy needed to raise the temperature of 1 kilogram of substance by 1 degree Celsius. State the equation that links specific heat capacity, mass, temperature change, and thermal energy. So we say change in thermal energy equals mass times by specific heat capacity times by temperature change. So that would be delta Q equals M times by C times by delta theta. Or if you do an aqua, I think they say delta T. Delta just means change in. Describe an experiment on how the specific heat capacity of water could be measured. Think about the equation and what measurements you would need for it. Now, as I say to my students, you should always base your explanation on a calculation. So obviously the calculation is this one above in this particular instance. So we're going to need to measure the mass. So use a mass top pan balance, 1 mark. To measure the mass, 2 marks. Use a joule meter to measure the amount of thermal energy. Use a thermometer to measure the starting temperature and the final temperature of the water. And then we can calculate the change in temperature by doing the final temperature take away the starting temperature. And then finally calculate the specific heat capacity by taking the change in thermal energy and dividing it by the mass times by the temperature change. So I just rearranged that equation there. So specific heat capacity equals the change in thermal energy divided by the mass times by the temperature change. Describe why a polystyrene cup is used. So they often put the water into a polystyrene cup. And that's to insulate the hot water, which reduces energy lost as heat to the surroundings. So that helps this value here be more specific, because all the energy goes into the water and it doesn't dissipate to the surroundings as much if the cup's insulated. Calculate the specific heat capacity of water when a student heated 500 grams of water. So that's our mass. The joule meter reading was 22 kilojoules, so that's 22,000 joules, and that's our delta Q. And the temperature change went from 20 to 30 degrees. So that change is 10 degrees. That's our change in temperature. So the specific heat capacity equals the thermal energy divided by the mass times by the temperature change, as I've showed you here. So just pop the numbers in for thermal energy, mass and temperature change, and out comes your answer. And that will be joules per kilogram per degree C. Make sure you know the units because they often ask you about them. The specific heat capacity of water is 4,181. So normally they're not as specific. Normally they just say it's 4,200 joules to get a kilogram of water to heat up by 1 degree. So always just remember that number because your answer is always going to be similar to that. Explain why results obtained from this experiment are likely to be higher than this value. Now, as I said before, not all of the energy is going to go into the water. Some of that will be lost to the surroundings as heat. So we think this number here is 22,000, but maybe only 18,000 actually went in to the water, and maybe 2,000 got lost to the surroundings. Define specific latent heat. Now that's the energy taken in or released when 1 kilogram of a substance changes state. If you looked at it on a graph, the temperature goes up, then it goes flat, then it goes up. This part here is the specific latent heat. The word latent is Greek. It means hidden. So hidden heat. Because if I'm still heating it, but you go, well, why is the graph not going up anymore? It's as if the heat is hidden. But of course we know that that heat is actually being used to break the bonds between the solid particles themselves, to melt the solid into a liquid. I've got another nice video all to do with that if you haven't got a clue what I'm talking about. State the equation that links change in thermal energy, mass and specific latent heat. So that particular equation is change in thermal energy equals mass times by specific latent heat. So that would be delta Q equals M times by L. So it's a lot easier than this equation up the top. Sketch a graph to show the temperature change when ice melts. Oh, well, that's what I've just popped up there. So a temperature versus time graph. So this would be temperature up the side in degrees C, and that would be time along the bottom in minutes perhaps. And the gradient goes diagonally from bottom left up to top right. Then it goes flat when it changes state, and then it goes diagonal again as it once again heats. And here's a core practical or 6-mark question or more to do with investigating springs. Pause the video if you'd like to have a go before I tell you the answers. So, how do we answer these particular questions? State the equation that links extension, spring constant and force. So force equals the spring constant times by the extension, often written as F equals Kx. Describe how to set equipment up to investigate the effect of force on the extension of a spring. So you'd have to hang a spring on a clamp stand, clamp a ruler next to the spring with the zero of the ruler at the top of the spring. So 0 would be there. Measure the original length of the spring with the ruler. So that would be the original length. Hang 1 Newton of force, which is the weight, onto the spring and remeasure the new length. So the spring might stretch down to there because it's got 1 Newton on. And you can see that's the new length now. And to calculate the extension, you do the new length, which was the purple, take away the original length, which I showed in red, and repeat this 6 times and plot a graph of extension against force, similar to this. Describe the relationship shown from the data collected. Okay. Well, as the weight is getting bigger, the extension also gets bigger. So extension increases as weight increases. Calculate the spring constant of the spring in the graph. So a hint would be think about the units. So the spring constant tells you how many newtons it takes to make the spring stretch by a metre. So we need to do newtons, so the weight, F, which is a force, divided by the extension. So because it's a straight line, you can pick any values you want. So for example here, I just picked 0.8 newtons because it was easy to see that the corresponding extension was 16. So 0.8 newtons divided by, now we need to convert the 16 millimetres. We need to divide that by 1,000 to turn it into metres, which will be 0.016 metres. And that comes out as 50 newtons per metre. Sketch on the graph the results of a spring with a higher spring constant. Okay, so this can be confusing for a lot of students. So if it's a higher spring constant, that could be perhaps 100 newtons to make it stretch a metre instead of just 50. And you'll end up with a lower gradient with a diagonal line from bottom left to top right through the origin, because you'll be getting less extension for the same force, as the spring will be stiffer due to the higher spring constant. So if it's going to take twice as much force to make it stretch, that would be something like, instead of just needing 0.4 newtons to make it stretch 8, it would need the 0.8. Okay, so what that's basically saying, let us explain that again. The first spring only needed 0.4 newtons to stretch 8 millimetres. If you've got a spring, and I just said it was twice as high, you'd need twice as much force to make the same extension. Calculate the spring constant when a spring is stretched 50 centimetres with 5 newtons of force. So rearrange the equation, K equals F divided by X. So that will be 5 newtons divided by 0.5 metres. So remember, we'd have to divide that by 100. 50 divided by 100 to convert it into metres. So the answer comes out as 10 newtons per metre. Calculate the energy stored in a spring of spring constant 0.9 newtons per metre when it is extended by 63 centimetres. So once again, we'd better divide that by 100 to turn it into metres. And then let's just use the equation. Energy stored equals a half kx squared. So that's a half times by 0.9 times by 0.63 squared, and that pops out as 0.178605. And if they wanted that to 2 significant figures perhaps, then the 8 will round the 7 up to 0.18. Well, I hope that's been useful. And as I say, it doesn't matter what exam board you're doing, they always have the same sort of 6-mark questions, the same sort of core practicals. Just make sure you know which core practical or which questions might pop up on your particular exam board, on each particular paper. Work hard, be nice, and bye for now.